So, we will now be looking at the last part of this course, which is going from single particle descriptions to actually trying to see if we can get a feel for how to model these systems as a continuum. Because in a lot of scenarios that you might be interested in, you may not be thinking of the problem at individual particle level, but rather you must be interested in a problem where this is a suspension, where you have many particles acting together in order to give you a macroscopic picture. Now, this occurs in a wide variety of problems, both in the built world as well as the natural world, and these are just some examples of flowing suspensions, and just for the visualization purpose I have chosen problems which have in some cases also interface present in it. And you can see in the top one what is known as a dam break problem. So, there is a break, you initially have a barrier confining a fluid with particles present in it, and as you release it, it flows down. So, this can be viewed as where you have a sediment laden flow front that is actually intruding into the surrounding. Similarly, you have these things known as granular avalanches. So, here the flow is more of granular kind, which means that the interstitial medium is air and only has a minor role in terms of the modeling the interaction between or giving rise to a dissipation in the problem. This is a scenario where in the bottom left is where you are pushing out fluid into another fluid, and the fluid that is being pushed out or that is being injected is a fluid which is again laden with particles, and what you observe is in the interface you have these nice fingering pattern. And if you are familiar with a little bit of this kind of a literature, this is classically known as a fingering instability or a Safman-Taylor instability, which usually occurs when you have a less viscous fluid that is displacing a more viscous fluid. So, you are injecting a low viscosity fluid into a medium of high viscosity, and you observe the interface actually developing these fingering pattern, something that is quite often seen in porous medium or similar related problem. But here what you are displacing is a particle laden fluid. So, effectively this has a higher viscosity than the surrounding, and yet what you observe is that the boundary actually starts to develop this nice interfacial pattern. And the same thing applies for flow of the kind like magma, where the lava that flows out is again laden with a lot of melt material. This is an example of again you are trying to pump in fluid. Basically this is an oscillatory, you can think of an oscillatory pressure driven flow of particles, and you are basically creating through this pump this oscillatory pressure gradient which drives the flow, and as you image it, what you observe in the central line velocity, that after a certain number of period of oscillation the flow starts to develop this patterns which are indicative of some kind of an instability that is showing up in this problem. Like if you were to repeat this exercise in absence of particle, you would not be seeing any such phenomena. You would just be observing, because this is Reynolds number which is low enough that there is nothing particularly that happens in this problem. But when you try this out, when you do this with presence of particles and you are viewing this as suspension, the scenario is quite different. In the same way, this is a rolling drum, and some of these problems are again motivated deeply by engineering problems. So, you have a drum that is partially filled with particles and fluid. So, it is a suspension, and then you, as you start rolling the drum, as you start spinning the drum, at a very low rotation rate, initially you would observe just a uniform coating of the interior of the drum. But then as you do higher beyond a certain threshold rotation, you would actually start seeing that there would be these band formations that would occur. So, you would have particle deficit regions and there will be particle rich regions that would occur. So, the film that is coating the interior of the drum actually develops a and instability which is in the span direction. And again this is something which would only appear when you have particles present in the problem. So, these are again reasonably low Reynolds number, that inertial effects which are typically studied when you think of instabilities do not occur. This is something like a conveyor belt problem. So, you have a liquid layer which is sheared from both sides by two plates or two belts which are moving relative to each other. So, you have one belt which is moving, let us say, towards the top, and the other surface which is moving towards the bottom. So, if you did not have any particles, what this would do is it is going to create a shear flow. You would get a velocity profile that would look something like this. This is what you would observe. Now, what you are seeing here is there is a free surface, the surface is actually in the plane. So, when you have particles present in this problem, you start seeing the surfaces developing corrugations or roughness. So, as you are doing the same exercise and you keep increasing the volume fraction of the particles, you start observing that there is an increase in the surface roughness. And as you can automatically start to imagine that this plays an important role when you are thinking of any problem, and most problems that where you are dealing with fluids in either the chemical industry or the pharmaceutical industry would invariably come with some dispersed phase. And so, if you are actually getting these kind of patterns, if you are getting this kind of disorderly behavior of interfaces, that can often be undesirable. And you can start asking the question that if these particles are trying to poke through the surfaces, what would be the competition between the amount it tries to poke in with respect to the surface tension that is there on the surface. Again an experiment not exactly of the same kind, but involving a free surface. So, you have a gravity driven flow. So, you are draining liquid on a plate and the plate is inclined. So, the fluid film actually drains down. Now, this kind of a problem is reminiscent of something that you might see on a rainy day where water is trickling down a glass plate or water goes down a gently sloped road. You will observe in such scenarios there will be waviness on the surface, but typically the Reynolds number at which this waviness comes up, that Reynolds number depends on the inclination, and for the experiment that was tried out, the Reynolds number here was extremely small. And when I say Reynolds number, this is the Reynolds number based on the thickness of the film, not at the scale of the particle. At the scale of the particle it is obviously Stokesian, but even at the scale of the film thickness with respect to an average velocity, it is a very low Reynolds number film that is trickling down an inclined surface. And what you observe is with increasing volume fraction, the surface starts to develop a lot of roughness. The surface starts to develop basically various kinds of features which is increasing with increasing volume fraction. So, the reason for showing all of this is a lot of these problems you will not be able to understand or address from the picture that you have learned from a single particle level. A single particle level description is not going to be sufficient to explain whatever you have observed here. So, you need a macroscopic picture, you need a picture which is going to treat this as a fluid at the continuum scale and viewing it from that particular description. So, what I will touch upon in today's lecture is going to be a very brief summary, because this is again a topic by itself which is very vast, of how do we go about modeling and studying the rheology of suspension. This is a vast topic with extensive studies that have come over several years in the past, and again in that you can have various kinds of classification. So, you can start from scenarios where you were thinking of dry grains. So, dry grains are, you think of your sand clock, that is a dry grain, right. There is the intermediate medium has just air in it, there is nothing, no liquid that is wetting those grains. So, that is what is your dry grain. Then you have your viscous suspensions, which is basically to say that there is a liquid that is there in between. Then as the particle Stokes number starts to become important, as it starts to increase, you are going to have competition where you can have viscous and inertial effects coming in together, and then you can be also looking at cases where the particles have some kind of an attraction in them. So, these are cohesive grains. So, you can have a lot of problems involving sediments and otherwise where the particles can flocculate or particles can basically agglomerate, and so you are studying a suspension where besides everything that is happening in the aerodynamics, you can also have this inherent cohesive nature of your problem. So, this becomes important also in the context of a lot of pharmaceutical problems, where what you are when you are trying to make a tablet, usually when what goes into making that process sometimes can be dealt with problems where you have the medium, the dispersed phase being cohesive in nature. And almost everything that I am going to discuss here, I will just focus on the viscous part, but whatever I have said here, this is assuming that the driving mechanism or the shear rate is a constant. The picture becomes significantly more complex if we are going to move away from a steady shear forcing. So, the part which we are going to touch upon is the part which has to do with viscous suspensions. So, that is the only part that I am going to look into, and this is revisiting what we have already discussed earlier, that if we consider just the example of a steady shearing problem, where you have a shear flow that is given by a constant shear rate, we know that there is a time scale in the problem which is the inverse of the shearing rate, that is the flow time scale, and then you can have a whole multitude of different other time scales. So, for instance, you can have a viscous time scale that is given by the particle size squared by the kinematic viscosity. This gives me a time scale over which momentum diffusion actually occurs. So, we went through this in the previous lectures by saying that if the particle were to move with a velocity u at some later time, if it was starting out from rest, then the drag force acting on the particle will not be instantaneously related to the particle velocity at that instant, if you account for the fact that the viscous time scale is not infinitely smaller than the flow time scale, which is basically accounting for that there is a length scale over which you will have a steady Stokes description, and beyond that you are going to get the unsteady description. Now, this again applies to the terminal velocity problem, where you can ask the same question, that how long would it take for the particle to achieve a terminal velocity. Now, we also encountered similarly the other non-dimensional number, which was the thermal time scale that was given by a square by d, right. So, where d was the diffusivity of the particle in the medium, flow time scale is gamma dot inverse, viscous time scale is a square by nu, relaxation time scale tau p is rho p a square by mu with a numerical factor. And then when you take ratios of these various different time scales, you encounter the three key non-dimensional numbers that are very important for single particle description. You have the Reynolds number, you have the Stokes number, you have the Peclet number, and the picture that we discussed was that at large Reynolds number you are going to get bubbly flows. If you are moving along the axis of Reynolds, you are going to get a bubbly flows in those problems, because the particle density is negligible compared to the fluid density. That is the Reynolds axis. Similarly, the Stokes axis is when the particle density is infinitely larger than the fluid density, and you get the granular flow. And then there is the inverse Peclet axis, where if you move towards smaller and smaller values of Peclet, which means inverse Peclet is large, inverse Peclet is large, then you encounter scenarios where thermal fluctuations are very important. So, this is the primary picture that we have of the diagram for studying single particle dynamics. You have granular flows, you have bubbly flows, you have suspensions which have thermal fluctuations being pretty dominant. So, colloidal suspensions, this is an example of fat globules in milk. If you actually can see, there is a motion that is happening for those fat globules that are occurring, and those motions, as we were trying to discuss earlier, is the Brownian motion that is undergoing. There is no imposed shearing flow that is happening there. Now, when volume fraction is included in the problem, so the previous picture was the single particle description. When you have volume fraction basically being non-zero, you have to account for particle interactions, and particle interactions can occur in different ways. So, you can think of them just the rigid particle interaction, or if the particles were charged, then there is a repulsive interaction that can happen because of the charge is present on the particle. So, you are thinking of charge particle interaction. You can have attractive interaction that can occur between the particles, which in one of the ways would be through van der Waals forces. The surfaces cannot be, in some cases the surfaces are approximating them as smooth surfaces is not appropriate, in which case you can have frictional interaction. You can also have these particles being so dense that they get jammed in the scenario, and you would have to then account for how the force gets transmitted in this kind of a jammed network. Obviously, this comes about with the picture that we are describing, which is the picture of there being a flow. So, if you were to impose a shear flow, then you can have the particles moving either towards each other or shear away from each other, in which case the lubrication problems that we have studied are important. The particles can have individual Brownian motion, which is something that individually we have studied, and then there can be additional effects of the particle free surface that can occur, and this is something which we will try to address towards the end of this lecture, that how can particles get distributed in a flow. So, this is basically all that is probably happening at the micro scale that manifests as something that you observe at the macro scale. So, it's a fairly hard question to answer, that how do you model suspensions accounting for all of these things that are going on, and the answer is, it's just not possible to put all of them together from a first principles approach. Some of them you can start taking a first principle approach and do it, but the large part of it also would come from various empirical model that are guided or informed by experiments. So, if you ask that what would be a good model, how do you search for a good model when you are trying to actually study suspension flows? So, the three key things, and this is where we are going to just restrict ourselves, is what would be the suspension viscosity, then the diffusion that we studied for particles. We basically said that the Brownian motion part, that the particle can execute some kind of a diffusive behavior. We will revisit that particular aspect, and the last part is the aspect that if I am trying to shear, I do this shearing experiment. If you have no particles in the problem, then the pressure that you experience in this shearing example is going to be isotropic. You will have a shear stress, but the pressure field would be isotropic. When you add particles here, the question is, would the pressure field continue, or would a proxy for the total pressure continue to still remain isotropic? So, for example, if I am trying to actually shear suspensions, do I experience also a force that is normal to the direction of motion? That is an example of you experiencing a normal stress. So, these are the three things which we will try to touch. Again, the caveat here is that these individually are very exhaustive topics. So, we will try to give a physical explanation of why some of these things occur, and then in some cases try to do a simple exercise in order to arrive at what their nature should be. Suspension viscosity, this is probably the easiest thing to get started with, and this is a part which we are quite well familiar with. We know that if you were to place a spherical particle of radius a in a background linear flow, the viscosity basically gets enhanced by a factor 5 Again, a small point here. I have mentioned 2 years here, 1906 and 1911. So, when Einstein did this calculation in 1906, he actually got 1 plus 5. So, there was an error in the calculation which he understood from knowing experiments done by Baselin, who was a student of Perrin, and then in 1911 he corrected it to 5/2. So, this is something which we have done in class. We have basically derived this Einstein suspension viscosity in class by using the idea of a stresslet. So, what we said in class was, if I write down the particle stress is expressed as the number density for the particles multiplied by the stresslet, and this object, the angle bracket, is what is an ensemble average. Okay. So, if I say in class, in the previous exercise when we did the Einstein calculation, we said this can be approximated as S of the single particle. And what was the single particle stresslet? 20 pi by 3 mu a cube E. So, we use this in order to find out what was the correction to suspension viscosity. So, now if I have to compute the particle stress, I need to say that can I approximate this as the single particle value plus an additional perturbation that is there to the single particle value. See, this object we had written down in principle can be computed numerically if you know the flow field. So, you have a collection of particles, you numerically solve for the problem and you can numerically find the stresslet. Now, if I ask the question that I want to find the next correction to my suspension viscosity. So, you can then say, when do I find that correction? At what volume fraction should I find the correction? So, if you place these particles and just without any particular physical reason, I think of a unit cell which has a single particle surrounded by neighbors. So, what would be the separation between the particles? How do I find that from volume fraction? So, this L is approximately 1/3 of the cell volume, right. If I say that I have defined a unit cell where there is a single sphere and at all the corners, basically I am placing its neighbors. You can choose different arrangement. I am basically choosing a simple cubic arrangement. You can come up with more exotic arrangements. The answer does not change a lot when you are thinking of this first level picture, that the separation between the two neighbors will scale 1/3 with the volume of the cell, right. Now, what is the volume of the cell? The volume of the cell is going to be inverse of the number density. What the number density is? Capital N by V, right. The total number of particles divided by the total volume gives me the number density. So, which means that the cell volume, if you think of the total volume, is actually you do this tessellation exercise. You have the total volume, you break it into small cells. So, the volume of an individual cell is the total volume by the number of particle, which means the cell volume is going to be inverse of the number density to the power 1/3. Now, what is number density? Number density will be 4 pi by 3 right. Number density is volume fraction by the volume of a single particle, right. Volume fraction phi is total number of particle into volume of a single particle by the total volume. So, this is number density into 4 pi by 3 a cube. So, the separation is going to scale as a phi to the power minus 1/3. That is the interparticle spacing. So, if phi is around 0.1, 10% volume fraction, what would be L? A into 0.1 raised to the power minus 1/3, which is approximately 2 times A, which means the spacing between the center to center is 1 diameter. That means they are almost coming close to touching, right. So, at a volume fraction of 10%, you will have significant influence of all the neighboring particles velocity field on each other. You cannot ignore interaction. So, the exercise here is basically trying to tell you that when you say volume fraction is 10%, that means interaction is important. You cannot ignore interactions. So, if interactions are important and I have to basically capture the effect of interactions, how do I go about doing it? So, the idea is I want to find this quantity. So, which means I am basically after the thing that I am more interested in is trying to find out that what is this term. To find that term, I need to find this 2 particle stresslet. So, the 2 particle stresslet, when I am going to do this ensemble averaging, what I need to do is I need to find the disturbance stresslet from one particle on the other and then average it by saying that let me place this sphere at x naught with respect to the sphere. What is the probability? So, given that one sphere is at x naught, what is the probability of finding another sphere at a distance of r? And then I am going to average the disturbance from the other sphere. So, imagine this is your reference sphere and each of these other spheres they are going to create a disturbance. The stresslet that is created due to the velocity field from the other spheres need to be averaged with a probability which tells us what is the probability that I find a neighbor at a distance x naught plus r if I was located at x naught. It is a conditional probability. Now, how does this scale? What is the stresslet on the reference sphere? So, this is my reference sphere due to the other spheres. So, if you draw this picture, I am going to draw all of them as points. So, this is the reference sphere 1 and then I am going to draw the other spheres as points 2, 3, 5. Each of these spheres are in a background flow which has a straining part E infinity, correct. So, imagine that there is a linear flow in which the sphere 2 is present. Now, what will sphere 2 do when it is present in a background linear flow infinity? Just think about just sphere 2 right now. Sphere 2 is in a flow field which has a straining component E infinity. Now, sphere 2 is force free and torque free. Should there be a disturbance? Think of a single particle problem. Do not right now think of the 2 particle problem or interaction problem. Imagine sphere 2 in isolation. So, if sphere 2 is in isolation and it is present in a linear flow which has a straining part, that is E infinity, will it create a disturbance if it is force free and torque free?
Yes.
It will, right? Why?
Because it have to resist the rigidity.
It has to maintain its rigidity, it cannot deform. So, it is going to create a flow field, and we know that flow field is going to basically act in order to oppose what is going on, right. How does that velocity field decay? Far away in terms of r, how does it scale? It scales as 1 over r square, that is the stress led velocity field, right. So, there is a 1 over r square velocity field contribution that is going to come from all the other spheres. Now, the question is, what is the stresslet that is created for sphere 1 due to these 1 over r square velocity field? That should be 20 pi by 3 mu a cube and E perturbation at sphere 1, right. E perturbation is the rate of strain of the disturbance field of sphere 2, sphere 3, sphere 4, sphere 5. Because sphere 1 is embedded in a disturbance field that is created by sphere 2 in the background flow, sphere 3 in the background flow, sphere 4 in the background flow, sphere 5 in the background flow. So, each of those flow fields, individual disturbance flow fields, are going to go as order 1 over r square. So, their respective strain component is going to go as order 1 over r cube. If the velocity goes as 1 over r square, the velocity gradient and the strain component should go as order 1 over r cube. So, in this, the strain part, the disturbance stresslet part should have a term that is 20 pi by 3 mu a cube and an order 1 over r cube term. Now, if I say the probability is uniform, which means what is uniform probability? If the probability is uniform, then it should be equal to n, right. The number density, the probability is equal to the number density if it is uniform everywhere. If the particles are uniformly distributed, then the probability of finding a neighbor is obviously the number of particle per unit volume. This is not the probability, this is a probability density. This multiplied by a dr basically gives you the probability of finding a particular neighbor between the location r plus and r plus dr. So, in a shell of r and r plus dr, how many particles are you going to find? That is going to be given as p times dr, which gives you, which is the number density. So, p is equal to the number density. Okay, all good. So, I can write the PDF, the probability distribution function, as n, and I am going to write dr as r square dr. So, everything looks okay, right, in order to compute this correction. I have a term that is 1 by r cube, I have r square, I have dr, and then an integral. Is this integral well behaved? This is dr by r. So, dr by r will be log, it will go as log r. So, it depends on what is your integration volume. You can consider different kinds of integration volumes and you will get different answers. So, this is what is known as a conditionally convergent integral. So, we are stuck with in a place where we do not know exactly how to find the next correction to the viscosity, because we are getting this kind of a complication where we cannot compute the average contribution to the stresslet due to two particle interaction. It is a bit of a a pain right now. So, to resolve the pain, we go back to what we did 2 lectures back, which is look at the two spheres, let this be sphere 1 with a position vector r1, sphere 2 position vector r2, and for simplicity I am going to consider both to be equal, and the separation vector is r. So, r2 minus r1 is equal to r. This is in a background flow which is u infinity is equal to u infinity of some 0 plus gamma infinity dot x. So, what is the relative velocity between the two spheres? Now, we did relative velocity in sedimentation problem, right. Now, before you do again anything to do with fluid mechanics, what will tensors tell us about the relative velocity? That the relative velocity should be linear in the velocity gradient. See, if you look at the geometry, there are these two spheres. I have considered them to be identical to keep life easy. There is one parameter which is the velocity gradient, and then there is another one which is the separation vector. So, the relative velocity should be proportional to gamma infinity dot r. Correct. Actually, if you thought these were tracers, then what is u2? If you did tracers, what is u2? U infinity of 0 plus gamma infinity dot r2. U infinity of 1 is u infinity of 0 plus gamma infinity dot r1. If you just consider two fluid particles at location r1 and r2, their velocity is going to be the fluid velocity at those location. So, the relative velocity of u2 minus u1 is going to be gamma infinity dot r2 minus r1 or gamma infinity dot r. Correct. So, the relative velocity for these two sphere problem will have a dependence on gamma infinity dot r, but then this is a proportionality constant which would be a rank 2 tensor. So, u relative I is mij gamma infinity jk rk. What is the dimension of this object? It is dimensionless. Gamma infinity dot r is already a scale of velocity. So, mij is dimensionless. So, now if it is dimensionless, it can only depend on dimensionless variables, right. So, mij is only a function of r by a and r hat, where r hat is r by r. It will depend on the unit vector for the separation vector and the length of the separation vector scaled by the sphere radius. Now, this geometry of these two spheres, this is axisymmetric. You consider the two spheres, there is a symmetry axis passing through the center of the two spheres. So, about the separation vector, the problem is axisymmetric. So, if it is axisymmetric, what would Mij be? What is an axisymmetric second order tensor? Alpha delta Ij, or rather alpha r hat I r hat j plus beta delta Ij minus r hat I r hat j. That is the general form of a second order tensor. So, that Mij that you have there for the relative velocity will take this particular form. Now, can you find alpha and beta? So, one way to find alpha and beta is to solve this problem exactly, solve this two sphere problem exactly. Once again, just like the sedimentation problem, that is not an easy problem. It takes some effort to do that calculation, but you can try doing this using reflection. If you do this using reflection, what is U2 0? That is the isolated second sphere in the background linear flow. So, the sphere is force free and torque free. So, what is the velocity field of a force free torque free sphere in a background linear flow? So, in a background linear flow, a sphere which is force free and torque free should spin with the background vorticity or half of that vorticity and will move with the fluid velocity at its center, right. So, I can write this as gamma infinity dot R2, right. Directly I can write it as gamma infinity dot R2 about the center. So, the center velocity on the surface there is going to be a spin, but on the center of that second sphere the velocity is going to be gamma infinity dot R2. So, it is just like a tracer. The sphere in a background linear flow, when you use the Faxen term, del square of the linear flow is 0. So, it will basically be whatever is the background linear flow evaluated at its origin. Similarly, U1 of 0 is also going to be gamma infinity dot R2 plus U infinity of 0. U infinity of 0 is some constant uniform flow. Now, we need to do reflection. So, to do reflection, I need to actually check that, imagine sphere 1. Sphere 1 is in a background straining flow and it is creating a disturbance that is trying to counter that deformation that the background flow is trying to do. So, this is going to create a disturbance which is U1I is, it will have a detailed form, but we can just take the leading order form, that is minus 5 half a cube xi xj xk e jk infinity by r to the power 5. If you take the total disturbance velocity, so if you go back to your notes on what is the disturbance created by a spherical particle in a linear flow, the disturbance will have a leading order form, that is 1 by r to the power 2. See, the numerator goes as r cube, denominator goes as r to the power 5. So, the term goes as 1 by r square. So, if you ignore the higher order terms, this is the 1 by r square term. The second sphere is seeing a background flow which is due to the disturbance from sphere 1, right. So, this is minus 5 A cube R I R j R k e j k infinity by r to the power 5. So, there is a feedback on sphere 2 due to the disturbance that is created by sphere 1. Now, obviously, there is going to be a Faxen correction of a Laplacian of this term, etc. I am just focusing on the leading order term. Similarly, U1 correction is going to be due to the disturbance that is coming from sphere 2 on sphere 1, which is minus 5 halves. This is a cube. Should it be the vector r, or with respect to sphere 2 it should be minus Ri minus Rj minus Rk e j k infinity, right. So, now the relative velocity is u2 minus u1 is equal to gamma infinity dot r, and then the minus 5 half, and then there is going to be a minus minus plus 5 half, both will add up and give you a minus 5 a cube by r square r hat I r hat j e j k infinity r k. Now, you can compare. This term goes as, sorry, this is r cube, because there is a 1 by r here, 1 by r here, which the r to the power 5 becomes r cube. So, this term goes as 1 over r cube, and this term, if you go ahead and do it, this term will go as 1 by r to the power 5. So, this is basically using a method of reflection to find the relative velocity. So, what I am trying to say here, that if you write this down, so the general expression for the relative velocity is gamma infinity dot r, and then with a negative sign a r hat plus b delta minus r hat dotted with E infinity dot r. So, this is the general expression, where obviously we calculated that a at leading order is 5 a cube by r cube, and you can similarly also try finding b, but they are purely functions of separation. Now, when you do this calculation, you can see that the relative velocity is crucially related to the nature of the linear flow. So, why am I emphasizing this aspect of the relative velocity? The reason is, in the calculation of your stresslet, and which is required for the viscosity, you need to find what is the pair probability. So, what is the probability of finding a neighbor given that you are located at a coordinate x naught, you are positioned at some point in space, what is the probability that you find neighbors around you? Now, this information is an easy information if you were doing a problem that was static, which means all your neighbors are stuck in space and they do not move anywhere. So, there is one sphere, and imagine that there are other spheres which I am drawing around, they are all stuck in space. So, there is a given probability density of finding your neighbors. But is this how it will be in the problem that we are studying? Why not? There is a background flow. So, we all are moving, right? There is a deformation that is going on. So, everyone is actually moving, and my relative velocity with respect to you, that depends on the nature of the background flow that is there, because you can see that this term is capturing the kind of background flow that you have. For example, if you take a linear flow that is a solid body rotation, what is this term? Zero. There is no strain, which means in solid body rotation both of us will exactly move without having any change of our relative separation vector. Whereas if you have a more complicated background flow, the relative velocity is going to be significantly. So, the relative velocity is a function of what kind of linear flows you have. You can have pictures which look like something like this. So, I am drawing with respect to a single sphere, or you can have, let us see, there is some space here. So, if I consider one sphere, with respect to this sphere, the second sphere can go along paths which look like this. So, this is something where similar to a planar extension. But if you have a simple shear flow with respect to this sphere, the second sphere can move along very different looking path, to the extent that they can also get into orbits. So, this is a simple shear flow, this is a planar extensional flow. So, for every flow there will be different kinds of trajectories of your neighbors with respect to your position, which means that when you are trying to calculate this pair probability is a function of your relative velocity. So, you need to find that pair probability when you are doing a particular kind of flow. So, this makes the effort more challenging. So, if you are trying to calculate your viscosity correction, what you get as the coefficient of the order phi square term, that term depends on what kind of flow you are doing. So, here you have these videos, at least the bottom one is playing. In the top one, this is in a simple shear flow. So, you have a flow in this plane. So, there is a second sphere with respect to the first sphere actually hops and goes around like this. Whereas, if it starts from elsewhere, the second sphere can get trapped in this kind of a closed orbit. So, it gets very complicated to the point that even this calculation of 5.2 can only be done if you say that there is some amount of Brownian motion in the problem, because when you have this kind of a closed orbits, it gets difficult to determine what that probability is. So, all of this is just to show that just that order phi square calculation, which is coming from the pair interaction, gets extremely involved when you are trying to extend it by looking for particle particle interactions. It is dependent on the nature of the flow field. The 5/2 phi, which I had mentioned also earlier, is not reliant on what kind of linear flow you are doing. You can do any kind of linear flow and it will be the same answer, but the next correction is crucially reliant on the nature of the linear flow. So, the microstructure, which basically is a word saying that how are these particles aligned or distributed with respect to each other, decides your rheology. And what is the microstructure? That is decided by the nature of the forcing. So, this is basically just the order phi square term. Now, this is a master curve for all the different kinds of experiments, simulations, all plotted together as a function of volume fraction. So, the curve that you have here, this is Einstein. The curve that you have here is the one that we discussed, that was done by Batchelor and Green in 1972, which was basically going through that exercise of asking that what is the relative velocity of two pair interaction problem, and then what would be the pair probability, and then using the pair probability you try to find out the two particle stresslet calculation. So, that is that line. And then you have this whole set of experimental data simulation. So, the Siru and Brady this is a many body simulation, You have a whole set of experiments that are present here. And what you observe is this is the volume fraction scaled by phi c. Phi c is your maximum packing fraction. How many particles can you pack in a volume? What is the maximum packing that you can obtain? Now this also depends on how you are packing them. If you think of an example of trying to put oranges in a box, do you just randomly dump oranges in the box or do you place them in a certain order? In which way would you manage to put in more number of oranges? Just throwing them in the box or putting them in a certain order? Putting them in a certain order, right? So when you want to achieve maximum packing, you would obviously want to put them in a certain order. But when you are doing this fluid mechanics calculation, you are not getting to choose how you are placing them. It is not a static calculation. The flow is going to dictate that as you keep looking at the problem at a higher and higher volume fraction, what would be the maximum packing that it attains. And the maximum packing that if you are in the smooth sphere case would be around 0.64. If the spheres were rough, then this is going to change. But what happens is that the viscosity diverges as you approach the maximum packing. That is the important point, that the system basically is going towards a very high value of viscosity as you start looking at denser and denser system. So there are different fits that are there. There are three fits which are plotted or given here. There is a Krieger fit, which is 1 minus phi by phi c raised to the power minus 2.5 phi c. The advantage of the Krieger fit is that if you take the limit of small phi, then this is going to go to 2.5 phi, which is the Einstein result. But a better fit is the Maron and Pierce fit, which is 1 minus phi by phi c with the inverse quadratic power. So this is basically the idea of your viscosity, that something as simple as the suspension viscosity can be very complicated, and especially when you are going towards dense limits where you do not have any theory. What you can do is you can get these various kinds of fits as you go to more concentrated suspension. But the point is viscosity is becoming extremely large. You can see the values here, right? This is mu scaled by the solvent viscosity. So it is starting from a value of 1 and it can go to at least 10,000 times larger than your solvent viscosity when you are still a little bit away. So phi by phi c equal to 1 is if it is around 0.64. If you are saying that phi by phi c is equal to 0.9, you are still a little bit away from maximum packing, and you have already gone 10,000 times more viscous response than what your underlying fluid viscosity is. So when you are loading your system, if you think of loading a system with particles, one of the key responses you need to capture when you are modeling them is that your viscous response is going to become larger as you have higher viscosity in the system. So Einstein viscosity is something that you can do in a very rigorous manner in class. The bachelor in green order phi square, as you saw in the last 1 hour or so, it's more detailed, and obviously I didn't derive that number. I showed you what the approach is, but I didn't go about actually telling you that what that number is going to be. So this is where I will stop today. We looked into the aspect of suspension viscosity. So primarily this actually says that if I am modeling my particle stress, the particle stress can be written as 2 mu times volume fraction into infinity, right. So this is what you can call as a quasi-Newtonian fluid. Now why do I say quasi-Newtonian? Because it is obviously Newtonian in this relationship, the viscosity is only a function of volume fraction, right. Now, if you say this volume fraction is it the bulk volume fraction with which you load your system, or is it the local volume fraction? So, if you say phi is equal to 0.2, but then when you are studying the problem with flow, you might probably find a higher volume fraction near one location and lower volume fraction in the other location. So, the local volume fraction can be quite different, and this could be due to the background shearing nature. So, in which sense phi itself is a function of your shearing rate. So, that is why I said it can indirectly depend on the shear rate, in which case it is not truly Newtonian. But otherwise this quasi Newtonian model is something that is sufficient if you are just trying to describe what is going on with respect to your shear stress. The other two parts which we will address in the next lecture is going to be on how the particles actually diffuse and what would be the normal stress. So, particle diffusion you are already aware from your Einstein picture, it takes this particular form. So, the question that we are going to be interested in is this diffusivity going to be capturing the disorderly motion of particles irrespective of whatever is the value of the Peclet number. Okay, good. So, I will stop here today.